So this is 9701 paper 41 May June 2023. Question 1 says group 2 nitrates decompose when heated. So describe how the thermal stability of group 2 nitrates changes with increasing proton number. Explain your answer. So we discussed this thermal stability of nitrate. Basically, there are two thermal stabilities, group 2 nitrates and group 2 carbonates. As we go down the group, for both, and I'm talking for both. So if we go down the group, so the thermal stability is going to increase. When the thermal stability increases, what does it mean? Let's suppose this is your nitrate. When it is decomposed, it's gonna give you the oxide of metal and NO2 and O2, right? So size of cation increases down the group. If you remember, the proton number increases as a result in increase in proton number, the total number of shell increases. When the total number of shell increases, so I can say that um, when the total number of shell increases, so obviously I can say the size of cation increases. As a result, the charge density would decrease. Like I mean to say that that particular cation, it may be calcium, it may be barium, it may be magnesium, it may be strontium, any of the cation from group 2. So its polarization would decrease. When the size of cation is smaller, so it would be attracting strongly. Okay. But when the size of cation is bigger, so its attraction power is lower. Its attraction power is lower. So when its attraction power is lower, so how it's going to break down the nitrogen and oxygen bond? So that's the reason I'm saying that if you go down the group, so the size of cation increases, so the polarization is going to decrease. So ultimately, I can say it's not going to break down the covalent bond. Hence, the thermal stability is going to increase down the group. It's mean that when you are going to provide heat, so they need more heating as you go down the group, because you have to provide more amount of energy to break the covalent bond. So that's the reason when something requires more energy to break down, so I can say it's more thermally stable. And when something requires less amount of energy to break down, so I can say it's less thermally stable. So less thermally stable means which can be easily broken down, and more thermally stable means which cannot be easily broken down. In B, they were asking equation. It's not only for copper. It's not only for copper. It's about all. If you have any of the metals, so you can see the same equation. Okay, the nitrates, when it's decomposed, so it's gonna give you the oxide of metal, and I can say the nitrogen dioxide and like oxygen gas. Then I have balanced this equation. Okay. In part C, they are saying copper nitrate is added to water. It's from the transition metals, in which I told you the different colors, the different compounds, the different solubilities. Basically, it's the copper chemistry. Sometimes we do the reaction of copper with NaOH, sometimes we do reaction with ammonia, sometimes we have few drops, sometimes we have concentrated solution like excess amount. So they are saying in the first, copper nitrate solid is going to add in water, so it's going to give you the solution A. Then when it is going to react with this ammonia, so it's going to give you the precipitate. Then you are going to add excess amount of ammonia, it's going to give you the solution C. And when we are adding excess amount of HCl, so it's going to give us solution D. Now he is asking, so that you are supposed to write down the formula of each of the following: A, B, C, D. Obviously, A would be this, because copper nitrate is solid. When it's going to like dissolve in water, so you will see that the water molecule would surround the copper ion, just like that. In this manner, the water surround the cation in this manner, since it has a positive charge. Okay, in this manner. So how many water molecules you have? You will say 6 water molecules. So I can say the formula would be copper H2O6. And the color of the copper containing species would be pale blue due to copper. It's only due to copper. And if you talk about B, when you are going to add ammonia, so it's precipitate. You know, precipitate means solid. So I can say that this is copper hydroxide. Copper hydroxide is insoluble in water. That's why they are saying it's PPT. So this is copper hydroxide. And the color of copper hydroxide would be the same. That is like the pale blue. Why? Because you can see in the first equation, the copper is +2, and in the second equation, the copper is again +2. And the ligand is having almost the same strength, you can say. So that's why the color is same, pale blue and pale blue. And if you can check C, you are going to add copper ammonia into copper hydroxide. You are going to add ammonia into this precipitate, excess ammonia. So ultimately, they are saying solution C. Like like I can say the PPT dissolved. The PPT dissolved to give a solution means that it is soluble in water. Okay. So I would be writing this. I would be writing this. Okay. So the color would be dark blue due to the presence of ammonia, the strength of this ligand. You know, the color of each and every ligand is depending upon the strength of each and every ligand. Some ligand, like different ligands have different strengths. So ultimately, when they would be attracting with the metal cation, so they would be having the different splitting pattern, the different splitting energies. And obviously they absorb different frequency of light, and they show complementary colors. In this way you will see different transition metals have different colors, because different metals have a different splitting energies. Different metals are going to combine with different strength, like different ligand with different strength. That's the reason, like each and every ligand would be showing you the unique color. Okay. So that's why sometimes we are seeing that this is pale blue, then dark blue. And they are saying we are going to add excess amount of HCl into this precipitate B. Again, the precipitate has been dissolved to give you a color, to give you a solution. So you have added chlorine. The size of chlorine is bigger. So that's why you will see that 4 chlorines are attached over there, and the overall charge is -2, because that copper is +2, and if you have 4 chlorine, each chlorine is -1. So -1, -1, -1, -1, that would be -4, and then +2, that would be equal to -2. That's the reason its overall charge is -2. Overall charge is -2, basically. Okay. So, okay. Now they are saying EDTA4 minus, it's a ligand. They are saying is a polydentate ligand. What is meant by polydentate ligand? What is meant by polydentate ligand? Polydentate ligand, okay? So, um, you can say the species that is going to donate more than 2 lone pairs. The species which is going to donate more than 2 lone pairs, more than 2 lone pair of electrons. So, and obviously it's going to make a dative covalent bond. Always you will see in a complex compound, there would be a dative bond between the metal and, you can say, a ligand. Okay. So if you can see monodentate ligand, it's going to make only one covalent bond. If you can see the bidentate ligand, so it's going to make double dative bond, like the two dative bonds. Okay. Or the third reason is that, okay, if you have a polydentate ligand, mean that it's gonna make more than two bonds. Okay, it may have three, four, five, six. If you can see, we have EDTA ligand. This is the structure for EDTA, ethylene diamine and tetraacetate. They are saying that circle on the structure, the 6 atoms that forms bonds with the metal ion. Obviously, we have to circle the area in which we can see the electron pairs. Obviously, for a dative covalent bond, we need an electron pair, because this is a bond which is formed by the sharing of lone pair of electron. Okay, so it's one-sided sharing basically. If you remember, in covalent bond, we used to say it was a mutual sharing of electron. It's not mutual sharing. Okay, and I can say this nitrogen is having one lone pair of electron, and this nitrogen, this oxygen, each oxygen is having negative charge. So of course, they would be having some lone pair of electrons. Okay, so they are going to make dative bonds. So we have to just like draw the circle. That's it. Okay, so we have 6 circles, which shows that the EDTA ligand is a polydentate ligand, or I can say it's hexadentate ligand. It has an ability to make 6 dative bonds with metal cation. When it binds with any metal, it's forming very strong bond. It's forming very strong bond because the metal would be surrounded by, like, is strongly surrounded by this ligand, that is EDTA. Okay, it's just like a crab basically. Or what is mean by coordination number? It's very easy. If you remember, in this complex, you can see 6. You can see 6. What does it mean? Like 6 water molecules are going to make 6 dative bonds with the copper metal. So this 6 is a coordination number. This 6 is a coordination number. So how can I define this coordination number? So you will say number of dative bonds formed between the metal ion and the ligands. That's called coordination number. That's called coordination number. Okay. Coordination number may be different with different compounds, with different complexes. Sometimes it may be 2, it may be 4, it may be 6. It depends. Then they are saying the complex calcium EDTA2 minus can be used to remove toxic metals from the body. Okay. Table 1.2 shows the numerical values for the stability constants for some metal ions with EDTA4 minus. Okay. With EDTA4 minus, or like the K stab values are given to you. Basically, K stab values decide how much the product is stable. Okay, so an aqueous solution containing calcium EDTA2 minus is added to a solution containing equal concentrations of chromium, iron, and lead. The resulting mixture is left to reach a state of equilibrium. State the type of reaction when EDTA, calcium EDTA reacts with chromium, iron, and lead. Obviously, it would be a ligand exchange reaction. Ligand exchange reaction. Or deduce the relative concentrations of this, and this present in the resulting mixture. Okay, so ultimately they are saying that FeEDTA, that is, you can see this, its K stab, it's the highest. So that's why I'm saying it has the highest concentration. And the lowest concentration, if you can see, like, what do you think? What is the lowest concentration? This, right? 1.1 exponent 18. Okay, so it would be the lowest concentration of Pb. And then we have chromium EDTA. So chromium EDTA, you can say its concentration is in between, right? Its concentration is in between. Chromium EDTA minus 1. Okay, so the highest one, this, then this, and then this. So just we have to look at the table, and then we have to decide which one is having the highest concentration and which one is having the lowest concentration. So why why FeEDTA, that is your product, is having the highest concentration. You know, it's more stable. That's why its concentration is higher. It's more stable. How can I say that it's more stable? So, you know, the K stab value would decide whether the compound is stable, whether the compound is, you can say, is having the highest concentration or not. That's it. So higher the value of K stab, stable would be the complex. Lower the value of K stab, less stable would be the complex. It's very simple. Then in E, they are asking the number of moles of water of crystallization in a hydrated ionic salt can be determined by titration using aqueous EDTA4 minus ions with a suitable indicator. Okay. They are going to do a titration with this ion and hydrated ionic salt. That is this. This is hydrated ionic salt, right? Let me write this. So it's going to do reaction with EDTA4 minus with a suitable indicator. 0.255 gram of hydrated chromium sulfate, that is this, is dissolved in water, okay? So, and made up 200 cm cube in a volumetric flask. 25 cm cube of this solution requires, I have taken 25 cm cube from the 100 cm cube of solution in a volumetric flask. I have taken only 25 cm cube for the titration, and I'm going to do reaction with 26.2 centimeter cube of 0.008 mole per dm cube aqueous EDTA4 minus ions to reach the end point. In every titration, you can see the end point by changing its color. If you can see the color change, so I can say that is your endpoint. Use the data to calculate the value of N in the formula of Cr2SO43.NH2O. You can see in the question they have given the volume and the concentration of aqueous EDTA. So I have found the number of moles of aqueous EDTA4 minus by applying the relation, that is mole is equal to concentration times volume. So the concentration is 0.008 and the volume is 26.2. So you have to convert 26.2 into like you can cm cube into the dm cube. So I'm going to divide it by 1000. So after solution, I would be giving this much moles of EDTA4 minus in 25 cm cube, because it's going to do a chemical reaction with 25 cm cube. I have taken this 25 cm cube from 100 cm cube solution. That was your stock solution. So if 25 cm cube, if 25 cm cube contains this much moles, so how much moles would be present if I have 1000, sorry, 100 cm cube of, you can say, solution, okay? So I have just cross multiplied and I got this value. So this is the number of moles of EDTA4 minus in 100 cm cube of solution. Since according to equation, the number of moles are same between EDTA and chromium 3 plus, it's mean chromium 3 plus, okay, in short. So the mole ratio is 1:1. So ultimately, I have told you that this would be the number of moles for chromium 3 plus ions. But I need to find out the moles of this. I need to find out the moles of this. So, like, I mean to say this. So ultimately, 1 chromium sulfate dot NH2O, 1 chromium sulfate dot NH2O, uh, when it dissociates, in this manner, it gives us 2 chromium 3 plus ion. It gives us 2 chromium 3 plus ions, okay, and 3 moles of sulfate ion. 3 moles of sulfate ion. So since the mole ratio is 1:2, I got the moles of chromium 3 plus ions, and I want to find out the moles of this. Since the mole ratio is 1:2, so this is the number of moles of the whole thing in which you can see there is an H2O. That's the main thing. So the mass of this compound is given, that is 0.255, and I got the moles of the whole compound, that is this. Okay. I want to find out the relative molecular mass. What can I do? It would be mass upon mole. Mass is 0.255 given in the question, or mole is 4.118. Exponent minus 4, that is this. I'm going to put the values over there and I would be getting the MR. And if you remember the same question you used to do in your IGCSE when you used to ask the value of X. So the total mass is 608 that I got. I'm going to subtract the whole value from this value. The whole answer is 608. The whole answer is 608, or this is the molecular mass of chromium sulfate, that is 392. After the subtraction, I would be getting any integer. So ultimately, I need to find out the value of n. So the H2 is multiplying over here. So then it would be dividing by, like you can say, this 18. Then I got this 12. So n is equal to 12. N is equal to 12. If you want to cross check this, put 12 as a result of n. So, and you are supposed to find out the molecular formula. If you are getting this, so means that your calculation is correct. Means that your calculation is correct, basically. Then they are saying a solution of chromium 3 plus and a solution of iron 3 plus have different colors. Basically, they are from transition metals. Explain why the two complexes have different colors. Explain why the two complexes have different colors. Okay. So I told you that we have different ligands with different energies, with different strengths. So each and every ligand is having the different energies, the different strengths. So ultimately, when it's going to react with, you can say, any of the metal cation, so they would absorb different colors. They would absorb different colors, obviously with different frequencies. And as a result, they would show complementary colors. Basically, this is the concept, color theory, as I told you when we were discussing transition metals. So the color, so the ions show, complementary colors. Complementary colors. They show complementary colors. So in this, like this is why you will see that different metals of the transition metals will show the different colors. Some, like iron 2 is green, iron 3 is brown, or you can say chromium 3, then you have nickel, then you have cobalt. So different transition metals have like different colors. I want to say this. Okay. So this is question number 1.